Hello everybody, this is the video clip for chapter 6, okay, but this one is for section 6.8.2. Previously, we are given a function of x and y, okay, in terms of z equals to f of xy, and then we are required to find the relative maximum or relative minimum without any additional conditions. However, for this clip, okay, we are going to have either z equals to f of xy, or we can go up to w equals to f of xyz, and you are going to find either a max or a min under some condition, but the conditions, okay, in this chapter, in this section, we are going to call it a constraints, okay, a constraint. For example, if we would like to find a relative extremum of this function w of xy depends on x squared plus y squared, okay, w equals to x squared plus y squared, subject to the constraint saying that your x plus 2y must be 3, okay, your x plus 2y must be 3. As you may notice that if you talking about this relation x squared plus y squared equals to one particular number, okay, it is an equation of a circle, right? For example, if w is 10, you may have this big circle, okay. However, if you talking about this big circle, okay, the point, okay, that is the same the point that is on this straight line, okay, which is the point that satisfies this constraint, okay, it is this one and that one, okay. You may got 2 points, okay, 2 points over there, okay. But then, I mean, if you looking at this smaller circle, okay, you may as well got another 2 points, okay, that is satisfying your constraint. Alright, okay, satisfy your constraint, and then your w is 4, okay. But if you look at this one, okay, look at this one, you are getting only one of the point over there, okay, the one point that is tangent to this circle, okay, and it also on this straight line, okay. So it's look like this straight line is the tangent line of this circle, and then this one is also one of the point, okay, that is satisfy your condition as well. So we are going to see which one will give you the relative extremum. But as you can see from this picture, if your circle is getting smaller and smaller, I mean smaller than this one, okay, smaller than this one, then it's not going to intersect this constraint line anymore, right? Okay, the constraint line will be here, and then the circle will be smaller, so it's not going to intersect the constraint line anymore. So this is the last circle, okay, the last circle or the smallest circle that will touch your constraint. So what does this mean? This one is the smallest circle, so it means that because the radius of the circle is the value of x squared and y squared, right? So it means that this circle gives you the minimum number of w. However, I mean, as your circle getting bigger and bigger, you got more and more value of w, right? And your circle can keep getting as big as you can imagine, okay. So what does this mean? It means that as your radius, so w can regard as a radius square, right? But it can regard as a size of the circle, okay. So as your size of the circle getting bigger and bigger, okay, then you still can find the point that is on this circle and also on this line, okay. So it means that you cannot reach any maximum of w because your circle can getting as big as you can imagine, okay. This is the idea. However, I mean, how can we find it? Okay, we can just go back to something that's very simple. For example, you can say that, hey, I mean, this x is actually 3 minus 2y, and then you just replace it, because what you need is the thing that on, the point x and y that is on this curve or on this surface, as well as the one that on this line, right, on this straight line. So as you plug in, you got x squared and 3 minus 2, because you are going to plug in into your x here. Okay, so what you end up with will be 3 minus 2y squared plus y squared. Of course, this one is happen to be a function of a y variable alone, so it is go back to a single variable function. Okay, and then to find the critical value, you can simply find your y prime, which is 2, and then 3 minus 2y. Okay, you just kick down this 2, and then a derivative of the inside plus another 2y. Okay, and then you make it equals to 0. All right, so this one you got a total of negative 12. If you just make it equals to 0, so you have 12 over here. Okay, you move the negative 12 to the other side. Okay, this one, the total of what? Of negative 4, and then negative 4 multiplied by negative 2, so you got 8, and this one you got 10y. Okay, so it means that your y is actually 12 over 10, or it is 6 over 5. Okay, this is your y, 6 over 5. And then you check whether this is the critical value, right? You check whether your critical gives you a max or min. So you are going to find your f double prime, okay, your f double prime from this one, okay, because here is already the 8. So you got the 8 plus the 2, okay, the derivative, the second derivative of your y, which is a 10. So it is positive, so it means that you got a upward shape like this. So of course this critical will give you a minimum. Okay, so as you have your y, then you can plug in here to get your x to be 3 minus 2, 6 over 5, which is 15 minus 12 over 5, is it? So you have 3 over 5 as your x. So it means that at this point, okay, the point that will give you the minimum value of w, your x is 3 over 5, your y is 6 over 5. Okay, something like that. And if you need to know what is the minimum value w under this constraint, you just plug in, okay, the minimum w is just simply 3 over 5 square and 6 over 5 square, and then you just figure it out what it is. So it is like a 9 plus 36, okay, and then over 25, okay, whatever it is, you figure it out. Okay, that will be your minimal w, subject to, don't forget that it is subject to this constraint. Okay, subject to this constraint. Are we all right? Okay, what if we have more than 2 variable at the beginning? Okay, you got 3 variable, and you need to find the relative extremum, okay, subject to this constraint, x minus y plus 2z equals to 6. Okay, so what we are going to do again, we will do the same thing. We are going to substitute. Okay, so you move these 2 terms to the other side, and then you are going to substitute your x by y minus 2z plus 6. So it means that right now you got y minus 2z plus 6 plus y square, or don't forget to have a square here, and the z square. Okay, if you want, you can do the completed square on the first term, but the same as previous. Okay, we are not going to do that kind of calculation, but we can use the chain rule to find the derivative, right? Okay, so this one we can look at it as a function of yz. So it's a function of two variables, which we have learned before. I mean, previously from like 6.8.1, or I cannot remember. Okay, so if you want to find the relative extremum of this kind of two variable function, first you need to do a derivative with respect to the one of the variable, right? So you have 2y minus 2z plus 6, and then a derivative of the inside with respect to y, which is 1, and then 2y, make it equals to 0. On the other hand, you need to find a derivative with respect to another variable z. So you got 2 again using the chain rule, plus 6, and then a derivative of the inside with respect to z. So you have -2, and then another 2z as well, equals to 0. And then this one will be easier to simplify. So you got 2 y's and 2 y's, a total of 4 y's. You have a negative 4z, okay, and then you got a positive 12. So you have -12 over there, is it? And then you have 2 y's again, and -4z and 2z. So you have -2z, right? And then you have 4. Oh, sorry, this one maybe it's wrong, because at the beginning you got a -4, right? So here you have -4y, it's okay, and then you got a positive 8z, so you have 10z in total. And here also -4 and 6, so you have -24. So you got 24 right there. You move it to the other side. Then it is not that difficult to solve for y and z, right? So you just do the addition among these two, because you have 4y and -4y's, okay? So what you end up with, it is 6z equals to 12. So it means that your z equals to 2, okay? Your z equals to 2, and then after you got your z, your y, you can just, plug in here. So it is this is a 2, so it means you got the -8. You move it on the other side, it is -12 and 8 over 4, okay, and you end up with -1. So it means that your critical point, it is simply y first and then z, okay? This is y and the z, all right? And then all what you need to check, okay, whether it gives you max or min or a saddle point. You check f sub y, okay, the same direction derivative, all right? And you can just simply look at this one, okay? And f sub y, you got 2 and 2, okay, which is 4. And another same direction, f sub z, you got you see this one, -2 and another -4. So you have 8 and 2, which is 10. And then f sub yz, okay, a different direction, f sub yz, you can just simply look at this one, okay, and it is -4, okay, all right, derivative with respect to z. So I mean, the one that you need to check is your same direction competing with different direction square. So your same direction is 40, and a different direction square, again, don't forget that you got a parenthesis, okay? So, and you don't really need to find the value. It is 40 and minus 16, so it is of course positive, right? So if it's positive, and I mean, it means that the same direction wins. So you just look at one of them. For example, f sub y, it is positive again. So it means that the shape is upward like this. So this point will give you a minimum. Okay. So it means that this critical point will give you the minimum value of w. However, I mean, all what you need, okay, is not only y and z but also the x. So it means that the x and the y and the z will give you a minimum of w, okay, under this constraint will be, of course, I mean, your z is -1, sorry, your y is -1, your z is 2. So just plug in here -1 and then a 2, so you have a 4, and then a 6, okay, so you have -5 and 6, so you got a 1 for your x. So this one will give a minimum of w under the constraint x minus y plus 2z equals to 6. Okay. What if you need to have your minimum value of w? Okay, what if you need to find a minimum value of w? Then a minimum value, so let me just use the black. The minimum value of w under this constraint, okay, subject to this constraint, it is what? 1 square, -1 square, and 2 square. This one is not that difficult to compute, right? It is 4 and 1 and 1, so you got a 6. That will be your minimum, and no maximum under constraint. Okay, no maximum under this constraint. All right. So this one is just like an introduction. However, what we are going to do, I mean, instead of using, you know, plug in and use the one that we have it previously, we are going to learn another techniques, okay, on how to find this relative extremum under the given constraint. So this is the so-called Lagrange multiplier. If you read it as French, then it is Lagrange multiplier. So it's up to your choice whether you use the English or the French. Okay, but he's a French mathematician. If we want to find the extremum of this function, subject to the constraint, so just be careful. This constraint must be in terms of g of x, y equals to 0. So if on the right hand side is not 0, you have to move it, okay, so that you can determine what's your g. So we are going to construct a new function capital F, which is the small f minus a lambda g, okay, small f minus lambda g, and then the critical points of the f, okay, of the f under the, this is not the, what should I say, this is not the common critical point, okay, but it is the critical point subject to this constraint as well, okay, the critical point of a small f subject to this constraint, obtained by solving the equation capital F sub x, capital F sub y, capital F sub lambda equals to 0, okay. This lambda is called a Lagrange multiplier, okay. So let us try to use this Lagrange multiplier to solve the same problem again, okay. So this one, we want to find a critical point of x squared plus y squared subject to the constraint, and just look at it carefully, look at the question carefully. What we can find is only the critical points, okay. However, if the function given has some physical meaning or some economical meaning, then after you got your critical points, then you may be able to interpret further what should be the, I mean, whether this critical point should give you a maximum or a minimum. Are we all right? So for example, this one, the constraint just look like this, okay. So it means that your g xy, it is x plus 2y minus 3 equals to 0, okay, and this one is your small f, right? So what you are going to construct is a capital F, which is a small f. Okay, the capital F, it is a small f and then minus lambda g. So it is a lambda and then your g. Okay, and don't forget to have your parentheses, okay, because this one is a negative in front of it, in front of the lambda. So what is your f sub x? The capital F sub x, it is 2x minus lambda, make it equals to 0. Your f sub y, it is 2y minus 2 lambda, make it equals to 0. And your f sub lambda, okay, it is actually it is a negative x plus 2y minus 3. Okay, make it equals to 0. Okay, one thing that you may need to keep in mind is that the way you write the x and the way you write the lambda, okay, you need to differentiate it carefully, otherwise it will be mixed up. Okay, and another thing that you may need to notice is that your f sub lambda, okay, your f sub lambda always gives you a negative of g, you see, a negative of g. But I mean, after you make it equals to 0, it will go back to your g itself. Okay, go back to your g itself. So this one, it means that your x, it is lambda over 2, your y, it is lambda, and then you can just, I mean, it is a single variable lambda, right? Or we can say a parameter. Then you can just plug your x and your y into that equation. So you have your x and 2y and 3 equals to 0. So this one, you got 5 lambda over 2, is it, equals to 3. So it means that your lambda is 6 over 5. Okay, so it means that after you got your lambda, you can go back to your x and your y. So if your lambda is 6 over 5, your x is 3 over 5, and your y is 6 over 5. So these are the critical point, okay, of the function small f. You see, a small f under the condition or the constraint x plus 2y minus 3 equals to 0. Okay, and to be specific, the point that we're talking about, it is x and y, which is 3 over 5 and 6 over 5. Okay, it is the same as what we have previously, you see, 3 over 5 and 6 over 5. Okay, however, I mean, the way we calculate, okay, it is simpler, okay, because you don't need to, you know, solve this one in terms of one of the variable, because sometimes this constraint is not that easy to be solved in terms of one of another. Okay, and then I mean, for some of you, you may say that, hey, it is a square again. I mean, if this small f, it is like pretty weird function, then it will be again more difficult to plug in this condition after you change one variable into another. Okay, so this technique, the Lagrange multiplier, help you a lot, okay, in terms of calculation. Well, right, for example, this one, you see, your small f is pretty simple, but your g, the condition, is somewhat not that simple. Okay, so let's take a look. This one, your g is actually x squared plus y squared minus 4. As I told you, your right hand side must be 0. So it means that again, just recall that a capital F, it is a small f minus lambda g. So it means that your capital F, okay, it is 3x and y and 6 minus lambda, and your g is x squared y squared minus 4. So what you need to find is f sub x, which is 3 minus 2 lambda x, okay, and make it equals to 0, and f sub y, it is negative 1 and 2y, 2 lambda y. You see this one, don't forget, equals to 0. And f sub lambda, as I told you, it is simply a negative of your constraint. Okay, and then after you make it equals to 0, it become, your constraint itself. Okay, so for example, this one, you can say that your x is a what? Your x is 3 over 2 lambda. You see, you just move this 3 and then you just divide it by a negative 2 lambda. And on the same token, your y, it is negative 1 over 2 lambda. Okay, you have negative as well. Then your x and your y depends on a single variable lambda, so you can plug in both of them into your constraint. Okay, then what you have, it is like 9 over 4 lambda. Okay, don't forget that you have x squared and then plus y squared, which is also 1 over 4 lambda, and then equals to 4. Okay, or you have 10 equals to 16 lambda. You just lambda square. Okay, you just move this whole denominator to the other side. Okay, so you have lambda equals to lambda square equals to 10 over 16. So it means that you got 2 of the lambda, which is plus or minus square root of 5 over 4. Okay, just like that. Okay, so it means that your x, okay, so you plug in your lambda over here, it is 3 over 2 and then plus or minus square root of 5 over 4. Let's do it one by one. So if your lambda is a positive first, okay, this one is if your lambda is positive, you have this positive square root of 5 over 4. Okay, or you have a 6 over square root of 5 for your x. Of course, for your y, it is negative 1 over 2 and a positive 5 over 4. Or you got 2 over square root of 5 with negative. Okay, however, if you talk about a negative value of lambda, okay, so this one is positive, right? If you're talking about a negative value of lambda, let me just do it here. Okay, then your x, it is 3 over 2 and a negative square root of 5 over 4. So you have negative 6 over square root of 5. And then your y, it is negative 1 over 2 and a negative square root of 5 over 4. So you have 2 over square root of 5. Okay, so that will be your another pair of x and y. So it means that the critical point, okay, so again, this is we emphasize again that this is the only critical point that we can have. Okay, you got 2 critical points. One of them, it is positive 6 over square root of 5 and negative 2 over square root of 5 and negative 6 over square root of 5 and 2 over square root of 5. Okay, this is the thing is only you got only the critical points. Okay, if you want to know whether it is given you a max or min, you need to analyze further, or you need to have some physical or economical meaning, okay, attached. For example, look at this one. Okay, it says the Cobb-Douglas production function. So this one is one example of a production function. Okay, for a particular manufacturer is given by 100 x raised to the power 3/2 and y raised to the power 1/2. Of course, for the production, it depends on a labor x, okay, and depends on a capital y, okay, and it says that a labor, okay, it will cost 150 per unit, and capital it is 250 per unit, okay. If the total cost of the labor and the capital together, of course, I mean, you don't have a infinite amount of capital, right? I mean, the investment money, so you need to have a limited, okay, of your cost of labor and capital together. It is 50,000. You need to find a maximum production level of this manufacturer, okay. So can you construct the constraint? Okay, this is the constraint. Can you see? This is the condition of your x and y, right? So from here, it means that, I mean, 150, this is only 1 unit of labor, but you hire x unit of labor, so you need to pay 150x. And also 250 is 1 unit of your capital, but you invest y unit of capitals, then you need to pay 250 multiplied by y, and added together, I mean, because you need it to be maximized, right? So even though you say that, hey, it is limited to 50,000, but you need to pay it all in order to get your maximum, right? So instead of using this inequality, we are going to make it equal to 50,000, okay, to 50,000. Let's say it this way. So this one is your constraint, okay. So of course your constraint must be in terms of equals to 0, right? So you just move that 50,000 over there. And don't forget that to construct your function using a Lagrange multiplier, you need capital F equals to small f minus lambda g. So here's your small f, x raised to the power 3 over 4, y raised to the power 1 over 4 multiplied by 100 minus lambda 150x and 250y minus 50,000, okay. Okay, just like this. So first, what you need to find is your f sub x, okay, which is, I mean, a little bit difficult. So it is 3 over 4 multiplied by 100, okay. So your 4 will divide 100 to be 25. So you got 75 x raised to the power negative 1/4 and y to the 1 over 4. And then don't forget this one, minus 150 lambda. You make it equals to 0. And then your f sub y, okay, the same thing. 1 over 4 will multiply with your 100. So you have 25 x to the power 3/4, y to the power negative 3/4, minus this one instead, 250 lambda. And then f sub lambda, as we told you, is going to be simply the negative of your g, okay, make it equals to 0. Can you figure it out how to solve it? Okay, can you figure it out how? Oh, sorry, this is 3 over 4, not 3 over 2. Can you figure out how to solve it? And can you notice something? You see, these two numbers, okay, if you add them up, it is a 1. So it has nothing to do with the fourth root, you see. And if you really look at it, this one has that kind of property as well, okay. So this one, you got the x raised to the power negative 1/4 together with x to the power 3 over 2, okay. Or you can just, let me just simplify a little bit. So it is 75 y to 1/4 x to the 1/4 equals to 150 lambda. This is one of them. And another one of them, your f sub y, it is 25 x to the 3 over 4, over y raised to the power 3 over 4 as well, equals to 250 lambda. So it seems that if you can flip this one, you see, if you can flip this one, okay, bottom and top, and then you just do it look like you do the cross multiply, you see, your y with the y, your x with the x, all the fourth root will be gone, right? So if you want to do it like that, you may think that, okay, this one can be written as y to the 3/4 25x to the power 3/4 over 1 equals to 1 over 250 lambda. Well, what is it that you do? You just do a reciprocal, okay, of your right hand side as well as your left hand side of the equation, you see. So this one you do the flipping the reciprocal. This one is also flipping the reciprocal. So after that, you will see that, hey, this one is one of your equation. This is the another one of your equation, okay, and you can do the right hand multiply. It must be equals to the left hand multiply. You know what I'm saying? Because both of them, I mean, this one, the left and the right are equals. This one also, the left and the right are also equal. So what are we going to do is to do like 75 y to the 1/4 over x to the 1/4. It is at the beginning equals to 150 lambda. And you are going to multiply with y to the 3 over 4 and 25 x to the 3 over 4. It is equals to 1 over 250 lambda. You see? So it's the left and the left multiply, okay, and the right multiply. They will be equal, they'll be the same. So this one, the lambda happen to cancel, okay, and then your 150 and 20 and 250, okay, the 10 is also cancelled. So your 5 will be 3 over 5, just like this, okay. And then this one, your 25 and 35 and 25 and 75 will cancel. And then you have 3y over x equals to 3 over 5, or you have y equals to 3 over 5x. This is a relation among them. Okay, this is the relation among x and y. See? And then which one that we haven't touched it at all, you see, in order to get your relation among x and y, you only using the f sub x and f sub y, you see, without using f sub lambda. So here the x and the y is there, and then you can, you know, rewrite your y in terms of x. So you just plug into your f sub lambda. So let me recall it here. F sub lambda, it is negative of 150x 250y minus 50,000, make it equals to 0. So you just plug in here. So you have 150x and 250 3 over 5y, 3 over 5x equals to 50,000. So the 10 cancelled. So 5 and 25. So you have 30x equals to 5,000. So it means that your x is 500 over 3. You see? Okay, so your x is 500 over 3. So after that, you can figure your y. Then your y is 3 over 5 and then 500 over 3, okay, which is 100, is it? So it means that the critical point okay, of your of your small f here, production, it is a what? 500 over 3 and 100. Okay, this one, don't forget, this is the labor, this is the capital. Okay, but because right here you are solving the problem concerning the production, right? Concerning the production, and then you already give the maximum constraint. You see, the maximum limit of your investment, it is 50,000. It is 50,000, and you can give no more. Okay, and after you given the maximum investment like this, you got this critical point. Okay, only one critical point. Of course, this critical point will give you a maximum, right? This critical point will give you the maximum production. All right, so it means that your maximum production, so this one of course will give you the maximum production under the constraint. Okay, and if you want to find what is the maximum, if you want to find what is your maximum production, then you are going to plug in this one, okay, into your small f, right? And then you may use your calculator to find your maximum output or your maximum production. Okay, all right, so if the thing attached with your economical problem like this, the critical point that you obtain usually will be the one that you're looking for, because you have only one critical point under this constraint, right? That will be the either the max or the min that you would like to find. Okay, right? If you obtain like more than one constraint, okay, for example, if you got your G1 as one constraint, your G2 as two constraint, is a second as a second constraint, you can construct your capital F by using a small f minus lambda 1 G1 and lambda 2 G2, and then solve this system to find your critical point again. Okay, and this critical point is a critical point again of a small f. Okay, by finding f sub x, f sub y, f sub lambda 1 and f sub lambda 2, make them equals to 0. Okay, so at this moment we are going to stop this clip right here, and then we are going to continue this section with a more and more word problem. Okay, so we'll see you then. Bye bye.